The partial differential equations that we want to analyze the function is going to depend in general on several independent variables. For example, for the one-dimensional bar we have just presented, it just depends on the temperature just depends on two independent variables, the position in the bar and time. So in the same way as we did in the first order ordinary differential equations, where the function they're just dependent on one independent variable that we were calling time, we're discretizing the time. We're defining a time step there. We have to do the same here, but both on the x and time. And if there are several other independent variables, we have to do the same in all the independent variables that we have. So here in this graph here, we are showing the phase space on x and time. On the x-axis, you have the space variable here, and on the y-axis, we do have the time variable here. As considering the case of the bar, for example, here we might consider that the x variable starts from 0 to the maximum length that we're going to call it L. And the time variable also starts at 0, and let's consider that the maximum time we're going to call it tau, just to distinguish from the t capital that we're using that for the temperature function. Okay, now that boundaries are going to defining the phase space that we do have, and now we have to discretize both x and time variables, so that we're going to consider, for example, we have to define previously what's the number of steps on the space variable that we are going to consider. Let's consider, for example, and x is going to be the number of space steps that we are going to consider. On the other hand, we'll have to do the same with time. So let's call nt the number of time steps that we are going to consider on the time variable. So that when you are specifying the number of the steps in each variable, then basically means that we are also specifying the time step, for example, delta t. Delta t would be therefore the whole range on time, which in this case it will be tau over the number of time steps, which is n over t. And the same we can say for the space step, that will be delta x will be the total range for the space. In this case, it's L over the number of space steps, and x. So therefore, we are in this way we are defining space step and time step. But of course, they don't have to be the same. The number it depends on the length of each on the range of each variable, and the number of time steps and the number of space steps, they don't have to be the same. They can be the same, but they don't have to be the same. So in this way, you are defining like points. You are discretizing both the space and both the time variable. And with this discretization, you are defining a mesh here, so that each point, like this one, for example, is characterized by a position here and a time. So, and its position is time can be defined, can be specified by an index. So an index is going to specify both the position and the time, because it's a position here, for example, on the x variable, can be specified with an index. So let's say, for example, this xn, for example, can be written this way. X naught, will be like the initial point plus n, which is this index here, times delta x. And this n will be running from 0 to the maximum one, which is nx. So that the number of points we do have here will be nx plus 1. And the same we have for the time variable, where here the index we are using to specify the time will be j. So all the points here on the time will be tj, will be the t0, which is actually the initial time, plus j times delta t. And again, j is running from 0 to nt. And the number of points you have here is nt plus 1. So the main aim, therefore, will be to evaluate what's the u function. In this case, we are going to call u is going to be the general function that we are going to evaluate. In this case, will be the temperature, but could be any other function. So we are going to call this general function that's going to depend on the two independent variables. We are going to call it u. And we have to calculate the u function at any position on the x variable that we're going to call xn at any time that is tj. So this is the main aim here, the evaluation of this one. And another, to make it simpler though, in order to use, we're going to use another notation for that, because as the index n is going to specifies the position and j specifies the time, we're going to denote this one by this expression here. So u sub n and j just basically means the u function evaluated at the xn position and time tj. So therefore, we will have to develop a method of finite difference representations of the equation differential or the partial differential equations in order to get actually the u function at any point here in the mass. And actually, besides the equation, it's important to have in mind that we are going to have several constraints. And these constraints are the following. First, we do have the initial conditions. And the initial conditions, we are going to use the pink color for that. And the initial conditions basically means that it's going to specify the u value for all the points here that is at t equals 0 or t0, depending on what's the time where the initial condition specified. So all these points here are going to be given by the initial condition. Besides that, another constraint, important constraint, is the boundary conditions. The boundary conditions will specify the value of the u function at the boundaries. At the boundaries are this one boundary, and there will be the other. So at any time, the u function it somehow will be fixed. Both the u function at the borders, I mean at the left border and at the right border, will be somehow fixed by the boundary conditions. So these are basically the two constraints we do have. These are the boundary conditions. These are the two boundary conditions. Besides that, you do have the initial conditions. And with these two constraints, the finite difference representation we'll have, that's the one we'll have to develop for the partial differential equations, we'll be able to get the value of the u function at any point here in the mass. And the strategy that we'll follow will be the following. We'll need some finite difference representation so that in order to start from the initial point here, we'll be able to, using the information we do have here, able to get the value of the u function at the next time step, and the next time that therefore we'll be able to get that information here, information of the u function at these points here. And then the second step will be the following, that once we know the information of the u value and all these points here, so we'll be able, using the finite difference representations, to get the information or the value of the u function at the next time step, and so on and so forth, so that we'll be able to fill the information of the u value on the whole mass we have defined here.